name's Caroline Sutton. I work at the Environment Agency and I lead on spatial planning. Can you go to the next slide, please, Victoria? So I'll just give a little bit of an introduction and context around the Environment Agency and our climate change role. We do an awful lot of things at the Environment Agency, but this is kind of slide sets out the spirit in terms of what we do, and we're trying to protect and improve the environment in all our various roles. So we try to help people and wildlife adapt to climate change and reduce the impacts of climate change on them. We improve the quality of our water, land and air by tackling pollution. And we work as part of the DEFRA group to create a better place for people and wildlife. So not just protection, but looking at enhancement as well. Next slide, please. So our corporate strategy is called EA 2025, and climate change is a real core part of our corporate strategy. And it's just, in a nutshell, really, we want to try to create a nation that's resilient to climate change. And so it is at the heart of everything we do. Next slide, please. Another relevant bit of context is the National Flood and Coastal Erosion Risk Management Strategy. We updated it last year, and the vision of the strategy is a nation ready for and resilient to flooding and coastal change today, tomorrow, and to the year 2100. So it's very much about creating resilience to climate change for the next 100 years. There are sort of 4 quadrants, if you like, on the left-hand side of our plan around adaptation, and one of them is around placemaking. And influencing placemaking through the spatial planning process is a key part of how we want to deliver our vision to manage flood risk and coastal change up to 2100. Next slide, please. So in my bit of the presentation, I'm going to talk about how the climate change allowances have been developed and what they look like, sort of setting it out in a very sort of beginner's way, because I know a lot of you might not be familiar with the climate change allowances. So just sort of setting the bar there. I know many of you will know about the climate change allowances, so apologies if it's stuff you already know. And then I'm just going to say a little bit about how the climate change allowances are used in practice for flood risk assessments. Next slide, please. So we produce climate change guidance called climate change allowances, and the reason for that is to help manage the impacts of climate change that we'll all be very familiar with. On the left-hand side of the slide, there are a few statistics around the impacts of climate change and quite a lot around how flood risk is going to increase. One point to note there, around 59% increase in winter precipitation. We've already seen a lot of flooding in recent winters, a 59% increase in precipitation during the winter is a very worrying statistic in the context of what's happened and what could happen. Also, another important statistic there is up to a 1.15 metre sea level rise by 2100. And actually what that could mean is that a 1 in 100 tidal event now could actually be once a year by 2100. So it's really important that the decisions we make now account for these future risks. And we do that through climate change allowances, as I've said. We actually produce 2 types of climate change allowances guidance. One called flood risk assessments climate change allowances. The links to this are in the slide notes, and I believe they'll be made available afterwards so you can find them. And that is the flood risk assessments climate change allowances guidance is around how you use climate change allowances for flood risk assessments when you're putting in a planning application or when a local authority is preparing a strategic flood risk assessment, so therefore the spatial planning process. And we also produce guidance for FCRM projects, schemes and strategies to ensure flood risk management infrastructure is designed to cope with future flood risk. And the link to that guidance is also provided. And I'm sure many of you will either use one or the other, or perhaps both in your day-to-day work. So the climate change allowances across both documents are actually quite similar, and I'll point out where they're slightly different, but they're both similar in terms of the numbers. They're just used in slightly different ways because obviously they're different processes. So we produce climate change allowances for sea level rise, and alongside those, we also provide allowances for wind speed, wave height and storm surge. We also provide climate change allowances for peak rainfall and for peak river flow. These are all in line with UKCP18, except peak rainfall. Some new research came out this year called future drainage. I think Louise is going to mention it in her slides. And what that means is we're still working through the process to update our peak rainfall allowances. Although I'd like to just add that, you know, the current peak rainfall allowances are fit for purpose and should still be used. In terms of where we have used UKCP18 to update our allowances, we use a high emissions scenario. This isn't any different to how we've created climate change allowances in the past. In the past, they have used a high emissions scenario when we updated them in 2016, and the previous versions of climate change allowances that came out published by the Department for Communities and Local Government, as they were known then, and now they're the Department for Levelling Up. So the high emissions scenario has a name. It's called RCP 8.5. It's probably sounds a bit complicated. It stands for Representative Concentration Pathway, and essentially an RCP is a concentration of greenhouse gas in the atmosphere, and they are produced for a low, a medium and high scenario, and they can be compared to UKCP09 as well, roughly. And the value in the RCPs now is that we can actually equate them to a temperature increase. An RCP 8.5, which is the high emissions scenario equivalent, equates to a 3.2 to 5.4 degree increase by 2100. The reason we use that emissions scenario is the UN Environment Programme GAP report says that we're currently on a trajectory of 3 degree increase by 2100, but that could be as high as 4 degrees increase by 2100. And RCP 8.5 is the only scenario that represents a 4 degree increase by 2100. So while we obviously hope much is done to mitigate the impact of climate change, to mitigate it and reduce it, and we have to be prepared that there could be quite high temperature increases by 2100, and therefore the decisions we make now need to prepare for that. Next slide, please. So I'm just going to do a couple of slides now showing what the climate change allowances look like. This first slide covers off the information we would use around tidal flood risk. So the top bit table there shows the climate change allowances for the Anglian area of England. We present an upper end and a higher central allowance, and the allowances are millimetres added on to the current sea level. For offshore wind speed and extreme wave height, they are percentages to add on onto current wind speed and wave height. And for storm surge, it's actually a millimetre increase that's added on, but only only where a high plus scenario is required. I'll come on to those in a second. As I said before, I would point out where the allowances are slightly different for FCRM schemes guidance. In the FCRM schemes guidance, we actually direct users straight to the UKCP18 user interface to obtain the allowances for the 12-kilometre grid. We use a simpler approach for flood risk assessments because a much bigger and non-technical audience use that guidance, and so we think directing them to the UKCP18 user interface is unnecessarily complicated, whereas for people using the schemes guidance, they can obtain a more precise figure, albeit it's not going to be hugely different. Next slide, please. So this slide shows what the climate change allowances look like for peak river flow and peak rainfall. For peak river flow, we recently updated our guidance. We used to provide peak river flow allowances for each river basin district. We now provide them for each management catchment. So it's a much smaller area of geography. So what that means is the allowances we provide are much more tailored to local characteristics than they were previously. Just to give a bit of a comparison, there were 11 river basin districts used before, and now there are 93 management catchments. And what this slide shows is what they look like for the Lower Mersey management catchments. They're provided on a map, and you click on the area that you're located in, and you get a little table of allowances. We provide allowances for the central, higher, central and upper end for peak river flow. And we provide it for different epochs as well. and that goes for sea level rise as previously and for peak rainfall. For peak rainfall, you can see the table at the bottom there. It's just one set of allowances for England, so not regionalised yet. Hopefully they will be when we update them. And we just present a central and upper end allowance for peak rainfall, again, for the different epochs. In terms of how the allowances are applied, you do your design flood risk assessment as normal, and then you add on the allowances to account for the impact of climate change for the lifetime of your development. Louise and Rob will explain a bit more when they get to their bits of the presentation. I said I'd say a bit more about credible maximum scenarios. In addition to these, we provide credible maximum scenarios, sometimes called H++ scenarios, and these are allowances that let you account for very extreme climate change that could occur in the next 100 years or so. They're important because the climate change allowances that we present are based on UKCP18, as I've said, and UKCP18 doesn't account for the full range of uncertainties. That's because scientists like to present information that is based on more certain information. And so we account for that through these more extreme scenarios. So alongside these allowances, there are extreme scenarios for peak river flow and for sea level rise and for storm surge. We don't provide them for peak rainfall at the moment. Just moving on to my final slide now about applying the allowances in practice. Planning policy, called the National Planning Policy Framework, is really clear that we have to account for the impact of climate change on flood risk. And it says that inappropriate development in areas at risk of flooding should be avoided by directing development away from areas at high risk, whether existing or the future. Where development is necessary in such areas, the development should be made safe for its lifetime without increasing flood risk elsewhere. So what this means when making planning decisions, it's really important that we think about climate change and the impact it has on flood risk when directing development to areas of lowest flood risk. So an area that's at low flood risk now might not be in the future, so we need to think about that. When you've located your development, you need to design your flood risk mitigation to keep it safe from flooding for its lifetime. And also you need to think about how you design your flood risk compensation. If you put development in an area at risk of flooding, you're going to take space for water to flow during the event of a flood away from, because obviously the development you've designed will be out of the floodplain, you would like to think, or will have been designed to keep it dry, so the floodwater has to find somewhere else to go. And then in designing compensation for that, you need to account for the impact of climate change and how that amount of compensation might need to be more in the future than it is now. So our climate change allowances provides guidance on how to use the range of allowances for sea level rise and peak rainfall. For peak river flow, we tend to advise use of the central allowance mainly. However, in some circumstances, such as for strategic flood risk assessments and for essential infrastructure, we advise use of the higher end allowance, the higher central allowance. And also we provide advice on when to use those extreme or credible maximum scenarios. For example, if you're going to design, create a brand new community in an area of flood risk, like an urban extension or a new town, then it's worth thinking about how climate change, those more extreme and climate change scenarios that could occur in the next 100 years or in the next few centuries, because climate change will continue for a longer period of time. It's worth thinking about those extreme scenarios in those particular cases. It's also important to consider them for significant infrastructure like nuclear new build or major power stations as well. That's all I was going to say. I'll hand over now to Louise.
Thanks, Caroline. Can I just check that I can still be heard?
I can hear you fine.
Yeah, perfect. I can hear you. Yep. Thank you all. So good morning. In this section, we're going to talk a bit more around the peak river flow allowances, their progression with climate science and how we apply them, including some of the complexities around that, and also some of the future considerations we are facing with the climate change uplifts. Move on to the next slide, please. To start with, I'd like to say that our understanding of climate change and potential impacts has progressed significantly over the 17 years I've worked at the Environment Agency. When I started, we were still applying a nominal plus 20% uplift across the whole country. Since the climate projections were updated in 2009 and more recently in 2018, we've seen a real step change and heightened confidence in the data we are producing within the field of climate science. One of the key uncertainties has always been the potential spatial variability of impacts across the country, which is why we moved away from the blanket approach to climate change and used the river basin districts, as Caroline has just mentioned, to kind of provide this better understanding of risk. And with UKCP18, we've taken that a step further, utilising the management catchments to get an even clearer picture of potential local impacts. We could have taken it further still, given the data is provided in 1 kilometre grid cells, but a discussion around usability and user experience led us down the path to the management catchments. Next slide, please. So in the next few slides, we'll look at how the data was produced and what that looks like spatially across the country. So the Environment Agency and the Scottish Environment Protection Agency commissioned UKCH to undertake a research project which modelled peak river flow impacts for all catchments greater than 100 kilometres squared. The methodology has been published in this paper by Alison Kay and others, and the modelling used the grid-to-grid national scale hydrological model, which runs on a 1 kilometre grid with various spatial data sets such as elevation, soil type, land cover, as well as daily rainfall and evaporation data. So next slide, please. The results of the modelling were collated and displayed using response services, shown here on the left, for every 1 kilometre grid cell with a catchment area greater than 100 kilometres squared. The colours indicate the change in flood peak, with purple being very high and grey being low. The X and Y axes represent the rainfall properties. These response services were plotted for 3 annual exceedance probability events and 3 temperature evaporation scenarios as well. They were then used to calculate the potential changes in flood peaks for the specific UKCP18 climate change scenarios, which are plotted on here as blue dots. The cumulative density function was then plotted as seen on the left, so you can read off the different percentiles of these projections, which are fed into the different uplifts that we're seeing with the management catchments on our on the web pages that we've set up to view these. So next slide, please. So this image shows the central allowance percentage increase in peak flow for the 2080s. And you can see there's a significant amount of spatial variability across the country. So broadly speaking, higher peak flow increases in the west and lower peak flow increases in the east, which shows the why we need to move to a more kind of spatial basis in terms of those uplifts. Next slide, please. So with the increased resolution of data, applying the allowances has increased in complexity as well. For most planning developments, the application is quite fairly straightforward, as given their likely size, they will fall for the most part within a single management catchment and be applied, as Caroline has already touched upon, in terms of we use the range of uplifts to show the range of potential risk going into the future for a development. However, within the Environment Agency, taking a holistic approach to flood risk management, we may need to model significant stretches of watercourse that cross several management catchments. The example in this slide covers a model of 4 watercourses that flows through 3 management catchments, with the blue star denoting the site of interest. The 3 management catchments each have their own set of peak flow uplifts and are significantly different, so we need to ensure we are setting a realistic picture of risk with our modelling. One of the key questions we need to ask is whether we use a fixed uplift approach, so all inflows are uplifted by the same amount, or a variable uplift approach and apply the relevant uplifts to the relevant inflow point depending on the management catchment that it falls within. Whilst using a variable approach may be more realistic, it can cause issues in terms of data management and understanding by our users. So it's something we've had to think through quite carefully. In this example, we used a fixed approach and refer back to the original 1 kilometre data set before making a decision. So it's still really important to utilise all the data available in certain cases. Next slide, please. We also need to be mindful of specific catchment types where applying the uplifts may not be so straightforward. In this example, the location of interest falls within a single management catchment, so should be fairly easy to apply on paper, but the agricultural nature of the catchment upstream of Crowland means that the floodplain storage has a significant impact on flow hydraulics. Because the model extends significantly upstream, the impacts of climate change are lost in the floodplain storage system before we reach the area of interest. In this case, we needed to increase the upstream flows to enable the full impact of potential climate change to be seen at Crowland. And again, it's about understanding the whole catchment. It's not necessarily just from a hydrological point of view, but also from a hydraulic point of view to make sure that we're using the best data. As you can see from these slides, the new uplifts bring with them some complexities. If we want to become a climate resilient nation, we have to base it on the best available data. Next slide, please. Whilst this discussion is mainly focused around planning and understanding risk, I thought I'd use the next slide to highlight how we're utilising the uplift in our flood alleviation scheme work. We need our flood alleviation works to be climate resilient now and for their entire lifespan. So climate change assessment is mandatory for most schemes. Once a design standard of protection has been agreed upon, the usual standard being protection against a 1 in 100 flood, the design is uplifted by the central allowance. This then becomes the minimum design standard for the ESSA and should allow for a reasonable tolerance in performance in most climate change scenarios in the future. Design is also tested against the high central allowance with a view that we understand the increased risk in this scenario and may choose to either build to this high level now or ensure current construction can be altered in the future to mitigate the risk if it is seen. This is what we call a managed adaptive approach. The final design will be tested against the upper end scenario. This is an extreme event, but will allow for contingency planning and aid our incident management activities, as well as the activities of our risk authority partners. So moving on to my final slide, please. So finally, I'll go over some of the work in the pipeline that we're feeding into over the next year or so. So whilst this update has taken place, we know others are on the way, and it's important to continue to develop how we account for climate change in our assessments, so they are as robust as possible. Caroline's already mentioned the future drainage project, and it's likely to lead to an update of our peak rainfall intensity allowances. As you can see, we're still providing this information as this nominal uplift for the whole country, but based on better resolution data, we may see a shift towards a more spatially robust set of allowances that will provide focus on rapid response and urban catchments where surface water risk is prevalent, and that will also bring us back into line with the peak river flow data sets. This may also impact how or when we apply the peak river flow allowances as we start to determine whether it is more sensible to use the rainfall uplifts for certain types of catchment, such as small catchments, and use this to define our hydrological boundaries. We're also in an ongoing debate around how we work with the 2020s time horizon and whether we should be reducing the allowances at this time frame to account for the 6 years of data we are including in our present day hydrological assessments. This is a complex discussion surrounding non-stationary data sets, and observing climate change increases our records, but hopefully the return from this discussion will ensure our guidance is as fully developed as possible. And obviously we're happy to share that with any interested parties once we get to that step in the future. Okay, thank you for your time this morning. I'll now hand over to Rob Quirke, who will speak more on the coastal climate change allowances.
Yeah, thanks, Lou. I'll just check everyone's okay hearing me.
Yeah, I can hear you, Rob.
Yeah, perfect. So my name's Rob Quirke. I work in the Coastal Evidence and Risk team at the Environment Agency. And over the next 5 or 10 minutes, I'll present an introduction to the coastal aspects of the UKCP18 data, which Caroline's already touched on, and then demonstrate how we use it in our coastal flood risk modelling at the EA, both for FRAs and for the EA schemes and strategies. Next slide, please. Yeah. The UKCP18 Marine report details the work done in the UKCP18 to assess the impact on our oceans. The overall trend shows an increase in sea levels with a range of impacts around the country. The diagram at the top right of the slide shows the difference between the different RCPs, so 2.6 and 8.5, displaying the sea level rise associated with the 5th and the 95th percentiles, which generally shows larger increases in the south than the north. The impact on meteorological patterns and wave climate is a very complex picture and contains large uncertainty. The report goes on to explain that there's no evidence for significant changes to future storm surge. Assessing the impact on wave heights also gives a complex picture with increases and decreases in the range of plus or minus 10 to 20%, varying by geographic location and between different models used in the analysis. At the Environment Agency, we've taken a measured but precautionary approach to include allowances for sea level rise, wind, wave, and surge increases into our models to assess the impact of climate change on flood risk. One thing's for certain, that as we increase sea levels, we will experience higher wave energy reaching our coastline, which will increase flood and erosion risk and test our coastal defences more frequently. Next slide, please. So what do the FRA allowances look like? Obviously, Caroline's discussed this a bit in her section as well. This is the flood risk assessments increases given in millimetres for sea level rise and storm surge as a percentage uplift for, wind speed and wave height. So storm surge, wind and wave allowances are national, and the sea level rise allowances are regional, loosely based on river basin districts, with a map available in the link guidance. So in the next few slides, I'll go through how to apply these allowances for flood risk assessments. Next slide, please. The table shown on the slide is one that we've actually created internally, but it's pretty simple, just taking the values that are given on the FRA guidance, and it shows the uplift each year in millimetres, and this can simply be added then to the water level from the coastal flood boundary data, which consists of annual exceedance probability water levels for the 100% to the 0.01% event at regular 1 kilometre intervals around the coastline. So in this tool, you just have to select your base year, which will be 2017 if you're using the latest coastal flood boundary data, required year in the future, and the area, so the highlighted yellow ones for this particular example, as well as if you're using the higher central or the upper end allowances. Obviously, our guidance refers to both. So in this example on the screen, where we want to calculate the increase in water level to 2120 from 2017, we need to add the 18 years worth of climate change for 2017 to 2035, and then add on to that the 30 years from 2036 to 2065, and then the 30 years from 2066 to 2095, and then the 25 years from 2096 to 2120. So that gives you an overall increase there with all them added together of 1.047 metres. And then once you've got this increase, it's simply a case of adding that onto the extreme water levels. Next slide, please. So this provides then the modeller with a peak water level, and they can follow the guidance set out in the Coastal Flood Boundaries report to create an extreme tide curve to provide time series water levels for inputs to their model. Assuming we have created our base year curve following the Coastal Flood Boundary guidance, we can simply add that 1.047 metres from the last slide to the base year tide curve as shown on the screen. And then this can then be run using flood modelling software, which is usually 2Flow for this, to calculate the tidal flood risk for the required events and epochs. An additional step is also required if also modelling the impact of waves and winds for a coastal location. Wave transformation models are used to bring the offshore wave characteristics to the shoreline. It is this part of the modelling chain where wave and wind allowances for climate change are applied, either the 5% or 10% increases depending on your required epochs. The wave transformation models are used in combination with wave overtopping and inundation models to then assess the flood risk. Next slide, please. So that was how you do it for the flood risk assessments. The next few slides, I'll just go through the slightly more complicated way of getting it if you're working on our EA schemes or strategies to download from the UKCP user interface. And so it's the same data, it's just rather than being selected by your region, you actually go on and pick an individual 12-kilometre grid projection. So it's slightly more detailed and more accurate to that specific area for these schemes. And again, as with the, this is the RCP 8.5 for the 70th and the 95th percentiles. So this provides more localized climate change increases in the flood risk assessments. So when you go onto the user interface, and once you've created an account, and logged in, you'll see the screen that's shown on the slide. So if from there you click on products, next slide, please. Once you're on products, which is this one shown in the top left, if you click on the marine projections tick box on the left-hand side filters, that narrows down the product list just to the coastal projections. And the one that we use is data sea level anomalies for marine projections around the UK coastline 2007 to 2100. Click on submit a request. Next slide, please. So this opens up a form with a map and some drop-down boxes. So then from the top 4 boxes shown on the left-hand side of this slide, only the scenario needs updating to RCP 8.5, as the others are already automatically selected. So then when you click on the map, you can zoom into your area of interest and select the relevant tile as shown in the middle of the slide. And then the boxes below the map can also be left as they are, unless you'd rather work with NetCDF than CSV files. And then click on submit. And next slide, please. So then the request will then start running, and after a while, which is normally less than a minute, but I've had it be up to about 5 minutes before, the outputs are ready to download, and you'll also receive an email with a download link. And you then have options for which file type you'd like to view, as shown on the bottom of the slide. Next slide, please. So then the downloaded data looks something like that on the left-hand side of the slide, with all your different percentile increases for that particular tile, and the climate change increases from 2007 through to 2100 for the RCP 8.5, 5th to 95th percentiles. So because we use the 70th and the 95th percentile, these cumulative increases can then be calculated to the required climate change date, and also to update the coastal flood boundary design sea levels to present day, as these are based on 2017 levels. In the 2 images on the right-hand side, the black font is from the download and the red text is my calculations. So this particular example shows present day levels to be 0.022 and 0.026 meters higher than that of the 2017 base year. So this needs to be added to your coastal flood boundary levels. And generally the larger of the 2 of these is used for present day runs, given that the differences at this short time scale are relatively similar and small. It's common to calculate the 100-year climate change increase, but the UKCP18 dataset only goes up to 2100. Therefore, to derive the 2121 levels, if you're doing 100 years from now, you should calculate the average increase of the last 5 years to add to each year beyond 2100. And this is stated in the guidance. So i.e. the average of 2100 minus 2099, 2099 minus 2098, etc. In this example, it gives increases of 1.051 meters and 1.419 meters for the 70th and the 95th percentiles to 2121 from 2017. Next slide, please. So then how do we apply the increases in our coastal models? So the increases are then simply added to the coastal flood boundary data set in the same way as discussed earlier in the flood risk assessment method. So in summary, for both FRA and schemes, we use coastal design sea levels from the coastal flood boundary extreme sea level data. It provides us with annual exceedance probability still water levels around the coast, as shown in the top right of the map, or top right of the slide on the map. And this information takes long-term data sets from our network of tide gauges around the UK to create the extreme water levels. And once we have this, as before, simply a case of adding the correct allowance from UKCP18 for water level increase onto the extreme water levels. And this provides the modeler with the peak water level, and they can follow the guidance set out in the CFB report to create an extreme tide curve and provide time series water levels for inputs to their model. And then wave transformation models are then used to bring the offshore wave characteristics to the shoreline if that's required for your study. Next slide, please. So the impacts of flood risk vary across the country depending on the geography and the location. So on the right of the slide, you see outputs from our Plymouth coastal model showing the historic Barbican harbour. So even with its current tidal defences, we can see a large increase in the 200-year tidal flood outline when we project it out to 2115. Other sites in Plymouth are more vulnerable to wave overtopping and have relatively little increase in inundation with climate change increases to water level. It is the increase in the wave energy and the overtopping that poses the risk at these locations, damaging defences and creating a hazard for people. In other areas of the country, such as on the south coast at Rye, which is shown on the bottom left-hand side of the slide, we see much larger increases of flooding with rising sea levels due to the extensive flat topography. Next slide, please. Hopefully that's provided a useful overview of how we use climate change data for our coastal flood risk modelling for both the FRAs and schemes, and how to download the data as well from the UKCP user interface. As you can see, coastal modelling is a crucial activity to inform us of the present day and future risk associated with our interaction with it. Thank you all.
Okay, that's great. Thank you to Caroline, Louise and Rob for their presentations. So we're going to go on to see if there's any questions in the chat. So Liam Nicholson's going to help me with the chat, if you're there, Liam.
Yeah, so I think one of the other two questions that first came up was, and I don't know, Caroline, if you could answer this, or anyone, to be fair, is about the guidance for fluvial allowances and probably guidance in general beyond 2100. Is there any guidance available for this in terms of looking at, the importance beyond 2100?
Hi, yes, I can answer that. So the current set of fluvial allowances go to 2125. So if there is a development with a 100-year lifetime, then we think it's appropriate to use the allowances that are presented in the guidance. Beyond that, there isn't any information in UK CP18 for rainfall projections beyond 2100 that can sort of direct that. So all we can do is recommend that an extrapolation exercise is undertaken and to try to understand how the trends up to 2125 may continue beyond that. And then once you've undertaken that extrapolation exercise, then the Environment Agency can take a look at it. Obviously, it's quite complicated, and so where you're going to extrapolate, then you've got to leave plenty of time for us to be able to have those discussions. So it's definitely not something that can be rushed. It's probably quite a difficult exercise. But Louise, I don't know if you would like to add to that.
And yeah, you've kind of given the answer I would have given Caroline. The fact that I think just to kind of add, certainly from a peak river flow point of view, there's a lot more uncertainty around the parameters we're working with and the impact we're going to see over the next kind of 100 years. They've taken that assessment further, I think, from a coastal point of view in terms of the sea level allowances, because we've got that more level of surety that we're going to see this increase in sea level rise. But from a peak fluvial point of view, it's a bit more challenging, which is why I think they tried to keep it within that kind of 100-year time frame. But obviously, as we continue to go through the updates to the climate projections, that will continue to push outwards. But I think they're probably just kind of mindful to not take it too far in advance because of the differences we might see. But say, as Caroline says, the current allowances take us out to 2125, which is obviously more than 100 years in the future, which should be okay for most of the development that we're undertaking.
Okay, great. So there's a question in here to do with the management catchment allowances being worked out for catchments down to 100 kilometres squared. And the question is one to use the management catchment fluvial allowances for catchments between 5 and 100 kilometres squared, and beyond 5 kilometres squared swap to the rainfall allowances? Not sure who's here. Louise, maybe?
Yeah, I can handle this one as well. Thank you. Yeah, so one of the challenges that we've had with the data is obviously that they do only run to the 100 kilometre to square catchments. So we've got some significant smaller watercourses that are maybe that aren't covered in terms of the location specific data. We took that into account when we were choosing what scale to provide the information at. So as it stands at the moment, for an area that isn't covered by the 1 kilometre squares, we'll use the management catchment that's relevant to it. So we are providing some level of information at that scale. This also ties in what I said at the end of my section in some of these conversations that we're having about how we're applying some of the allowances or the type of allowance that we're applying. The rainfall intensity information is generally only for catchments that are less than 5 kilometre, but we might start to expand that a little bit when we can start looking at some catchment types. We've talked about maybe looking at some research into this to understand the types of catchments and what the most appropriate allowances is. And these are what we're going to be looking at once we get the rainfall data through, as to whether we can set up a kind of flow chart to understand what allowance we should apply to what type of catchment or what size of catchment. But that's something we're working on currently.
Okay, thank you for that. So there's another question here, which is just regarding the published date for the peak rainfall intensities in the future drainage programme. Do we have any idea of when that's likely to occur?
I'm hopeful that it will be at some point next year. I've sort of worked up a plan. We just need to explore, do quite a bit of research to interrogate the data. The future drainage research results present a big range of options. So, for example, they present projections for different rainfall durations, so 1 hour, 3 hour, 6 hour, 12 hour, 24 hour, for different return periods, 3 year, 2 year, 100 year, and then there's a central and upper end allowance, and then we've got different epochs. So if we presented allowances covering all of those scenarios, we'd have a huge allowances table, and then we'd have to think about regionalising them as well. So it needs to be rationalised in order to be understandable and usable. And that's the task that's going to take the time, unfortunately. I'm hopeful that once we've had some discussions towards the end of this year and early next year, we will be able to confirm a timescale for update, and there will be, a period of time for people to be made aware and then for it to happen. So I won't say we're publishing the update next week, sort of thing. We will make the sector aware when we intend to publish an update. It won't be before the middle of next year. So I would I can't sort of don't hold me to 100%, but I'm hopeful sort of the second half of next year we should be able to publish an update, but hopefully early next year we'll be able to give you a more accurate timescale.
Okay, great. Thanks for that, Caroline. So there's a message from Marie Dale on here. Given the new peak river flow allowances did not use the new CPM from UKCP local, it would seem sensible that smaller catchments should use rainfall from UKCP local as used in future drainage, rather than the peak flow uplifts derived from the coarser scale climate model. It may also be the case that the CPM model could result in changes in peak flow in larger catchments, since convective events can drop very high amounts of rain. Would the Environment Agency consider using UKCP local output to sensitivity test this?
That's one of the things we're discussing at the moment in terms of how we want to use future drainage and the allowances that come from it for exactly those purposes. We haven't come to a conclusion yet, but I strongly suspect that there will be some kind of guidance on how to apply them for those scenarios. I don't know if you want to add to that, Louise.
Yeah, again, and that would have been my response as well, Caroline. It's the fact that we started discussion around what kind of research and testing we'd like to do in terms of the rainfall data. The reason we're having that conversation is that it's been raised that obviously there may be a more severe risk using the rainfall allowances than using the peak river flow, and this is why we want to make sure that we're giving the right advice as to how to apply and when to apply around what type of catchment. So again, this will just come out through the conversations that we're having and the research testing that we're going to be doing on the rainfall data. So watch this space.
Okay, thank you for that. So just another one here, which is there an easily accessible comparison between the UKCP09 and the UKCP18 data available?
In terms of what sort of, it depends what you're comparing in terms of, if you want to compare the scenarios, we can, I can send you something that shows a comparison that explains how UKCP09 was used and how UKCP18 has been used. So for example, for the peak river flow allowances previously, a medium emissions scenario was used for the central and upper end allowance, and a high end scenario for the high emissions scenario for the upper end allowance. The reason being was that because we weren't really sure what represented it previously. The allowances before that were based on what was thought to be a very precautionary approach at a high end, although it was a flat rate of 20%, and that turned out not to be particularly precautionary. So if that's the sort of thing you want to provide, I can also provide a comparison between the current emissions scenario and how they equate to the 09 emissions scenario. I can provide those two bits of information if that would help. I don't know if anyone wants to elaborate on the question.
I think Kirsty said that sounded fine, so I think it might be
okay.
I'll
send those to Victoria. Is that okay, Victoria? And you can share those with the slides. It'll just be sort of an extract. Okay. Yeah.
Great. Thank you. So I have a message. How do you apply the peak flow uplifts? Scale the full hydrograph or stretch the peak? Scaling influences the base flow and equally the volume.
That sounds like definitely one for Louise.
Yeah,
I'm a humble planner.
And I'm a humble modeller. Yeah, so I was just trying to find that in the chat. So is this around the conversation we were having to do with extending past 21-25? Because we don't necessarily have, it's not written down in any guidance as we looked at that, and I'd probably be looking to someone from a more hydrology background to advise. We know that obviously the change in climate change isn't linear, so we'd have to have an understanding of what we need to account for that. Is that, so I couldn't find the question in the chat to reread it.
That's just come to me directly, I think. So from someone called Mike. I'm not sure if you want to say any more about that, Mike, if you're there. No, doesn't look like.
No, but if that's not the right answer, then please, do raise it directly with us, and we'll get a hydrology bot to provide that answer if I've taken that in the right context, or the wrong context, should I say?
Great, thanks, Louise.
Yeah, so there's just a question from Chris Whitlow here, which is the one I've seen. I don't know, Victoria, if there's anyone else to ask, but if we go with this one first, which is were the percentage peak fluvial flow uplifts based on rainfall intensity uplifts filtered through grid to grid? I'm not sure who's best placed to answer that.
Sorry, can you say it again, please?
Yeah, so it's were the percentage peak fluvial flow uplifts based on rainfall intensity uplifts filtered through grid to grid? I don't know if maybe it's worth Chris just speaking up on that, and if there's any more context that can be added to that.
Okay, can you hear me?
Yeah, that's fine, Chris. Can you hear you? No
Okay,
problem.
jolly good. It's just that, I mean, in recent times, people have been using whole catchment rainfall models, and those ones, you need to use rainfall hyetographs to drive them. Now, we've always taken the view that we want to compare those with the equivalent flood flow uplifts from standard hydrology. But I was just wondering how the rainfall, whether the rainfall intensity uplifts were used as a basis for the flow uplifts, the increase in peak flow uplifts.
From my point of view, I think the answer to that is yes. I can double check. If you can email me the question, I can check with colleagues who work much more closely with the Centre for Ecology and Hydrology who did the work. But I don't know if Louise knows a bit more before we move on.
Yeah, we might need somebody like KTP to provide that, but they were certainly based on rainfall projection data. But we need to go back to the project team to understand what tests they did, whether that's something we might look to do in terms of the new rainfall data coming forward as part of our sensitivity testing and how to.
Yeah, I mean, it would be useful to know what data they used. That's all, because that would then be consistent with what the peak flow uplifts are telling us.
Okay, if you send it through, I will get an answer for you. Okay.
Just a point on that as well. Just a point on that as well. We'll try and those kind of information we'll try and distribute that as wide, with the wider audience as well, if it's appropriate. So, Victoria, I don't know if there's any more you've seen questions.
Yeah. So Mike's messaged me. Just wants to try. Do you want to speak up, Mike, again to see?
Can you hear me now?
Yes, we can. Yeah.
Perfect. I was on mute before. Sorry, I was talking to myself. The question about the scaling and stretching relates to all events up to, say, the 2080s. So the question is, do I apply, for example, 54% on every ordinate of the hydrograph, or just on the peak and the others being pro rata, such that the start and the end points are 0? Because there was, at one point, the Environment Agency was going to issue guidance on this, but I've not seen anything since.
I've not seen anything specific around that either, Mike. So do you know where or who mentioned that they would be sending information around from? I can probably check in with our hydrology team, because it sounds certainly like something that they would have been involved with.
We had a presentation through HS2 a few months back, I can't remember when, and it was mentioned then. But as I said in the original question, if you apply 7 or 54% to everything, it applies to the volume of the hydrograph. So when we're sizing compensatory floodplain and this sort of thing, it has a big effect. Whereas if you apply it just to the peak, because the guidance is this is the peak flow uplift, when is a peak not a peak? So is the base flow a peak? We've
had this question before, and I think I might have even sent you an answer. I think at the moment, my understanding is that the sophistication of the information that we have might mean that we're not able to be more specific. I think that's my recollection of the answer. But again, I think if we can pick that up, Louise, with hydrology colleagues, then then we'll get a better answer than what I've just given.
Okay, thank you.
Okay, great. And does somebody have their hand up there? Do I just see?
Yep, so it's Murray Dale. So Murray, if you just want to speak up if you can.
Thank you. Just in response to that last question, I think the idea is that the percentage uplift applies to the design storm. So when you're using the FSR or FEH approach, where you use say a 30-year or 100-year design storm, you apply that uplift to the total rainfall of that design storm. So it's just applied to a discrete event. So you're not uplifting the base flow You're just uplifting a single event. If you're engaged in trying to use continuous simulation where you're using long time series rainfall, then you need to look at other approaches. There are other approaches being developed for the water industry, for example, but they're not commonly widely available. I hope that helps.
I was looking at peak flow uplift, not the rainfall. So the storm doesn't come into it.
Well, so I think it's the same issue though, because if you've got that peak flow hydrograph, then you're applying the uplift to the peak total volume of the hydrograph. Sorry if I was confusing things talking about rainfall. It's the same issue. Mm-hmm. It's just applied to the discrete event, the uplift percentage, rather than the full hydrograph with all the base flow as well.
Okay, that's what I was thinking. Thank you.
Okay, great. So we are on midday now. We have just got one more question. If people are okay just to hang on and answer that one.
Yeah, that's fine.
Quite an interesting one from Rob Sweet. Is the Environment Agency having conversations with software providers on integrating these allowances within the software rather than the end user having to apply outside of the software?
Okay, so I don't. Sorry, go on. You go, Louise, because I was going to say I don't really get involved in the software end of things, to be honest. Yeah. So I was going to give half an answer.
we certainly have conversations with our suppliers and our vendors in terms of software updates, certainly around some of our key packages like Flood Modeler Pro and 2Flow. I think we have a forum session coming up soon, actually, where we're going to get together with the vendor to discuss what we want to see from future versions. So I'll definitely pass this on to, I imagine we'll have a hydrology representative on that who'll be able to raise that question directly. It's not something, we only have these forums maybe once a year, so they're not particularly regularly, but yeah, it's an interesting concept and certainly something we can have a chat with to our vendor.
Okay, that's great. So I think that's all the questions anyway. So just to say thank you again to our three presenters today from the Environment Agency, Caroline, Louise and Rob.